Section 6.8 is going to be the last section that we're going to do in this particular chapter. And the nice thing about this is, using it to finish up, it's a lot of the stuff that we did with transformations when we were talking about both linear functions and quadratic functions, as far as, are you taking an entire function times a certain factor? Are you just simply shifting it left or right, up and down? Are we reflecting it across the x-axis or the y-axis? Or are we going to, try to horizontally stretch or compress something? Now, again, this should be mostly review. We're going to transform these polynomial functions. The same rules apply. If you look at all this stuff, it should be very, very familiar. It should be something that you have in your notes already from back in chapter 5 and from either some of the earlier on stuff that we did when we were talking about linear functions. All the same rules apply. The thing you're going to want to keep in mind, like we always talked about, the most difficult one on this particular sheet, or the one that we probably had the most difficulty with in the past, is when we horizontally stretch or compress something. Okay, and just remember, it's kind of opposite. Say we want to stretch something horizontally by a factor of 5, like it says over here. Essentially what you do is you're taking the x values times the inverse of that particular number. So if we stretch by 5, we actually multiply all the x values by 1/5. On the other hand, if we want to compress something, compress something horizontally by a factor of 1/3, it would be 1 over 1/3, which essentially gives you 3, like it looks like over here. So remember, it's always kind of backwards. And just kind of think about it this way. If we stretch something vertically, we're more or less compressing something horizontally. Or if we stretch something horizontally, for the most part, that means we are stretching something. If we stretch something horizontally, that means we're compressing something vertically most of the time. All right, but again, you're going to want to refer to this particular chart. It's probably something you want to have written down on your sheet, because again, this column right here is essentially telling you everything you need to do to make these functions work, or how to transform them, translate them, whichever way you want to look at it, to get what you're being asked to do. Okay, now we're just going to start pretty simple here. Okay, we want to write the rule for the function and sketch its graph. All right, well, as far as sketching the graph, that's just a matter of kind of translating points, and I do have a graph that I'll pop up here shortly, but that's one of those things where just it's a matter of filling in x values if you want to figure out how your graph is going to work. And you can always check using a graphing calculator. So in this case here, it says g of x, the function that we want to achieve, is just a matter of taking f of x minus 2. Well, f of x up here is x to the third minus 6. So that's in place of more or less the f of x that's right here. And then we want to subtract 2 from it. Okay, so this is going to give me g of x, which is the new function I'm looking at here. So g of x, we can't do anything inside of the parentheses here. Okay, you can't combine like terms or anything. Okay, so essentially what we do is we just combine that -6 and that -2, and our new function, or the rule for our new function, is x to the third minus 8. Now again, don't get confused with the whole g of x, f of x thing. All this is saying right here is g of x, the reason we give it a different label is just simply because it's going to be a different function when we're done with it. Okay, you don't want to be using f of x for both this part and this part because it becomes a little bit confusing. Okay, so more or less that's what we did. Alright, now if you take a look at the graph that just popped up here, the blue line would represent your original function. Okay, the x to the third minus 6. The red line would represent the g of x function, which we just found, which you can see by looking at your graph. Alright, we just took the values of the first function and we more or less shifted it down. Otherwise, it's the exact same graph. Okay, it just is kind of centered in this case in a different area. Now remember, with quadratics it was a little bit easier, because when we shifted things up and down, left and right, we were more or less just shifting the vertex point. Okay, with these right here, there's not necessarily a vertex point. No, you kind of have this little bend in the graph right here, which in this case is centered on the y-axis. Alright, but you're just thinking about, we're shifting this graph down 2 units from what our original f of x function would look like. Okay, here's another example. All right, and I'll save that graph here for a second here. Okay, now with this one right here, okay, same idea. We're given a function to start with. All right, in this case, it says we want to go ahead and apply this transformation down to it, and we're going to call our new function h of x. Okay, so a little bit different with this one. We're taking some type of value and we're filling it in with the actual x. So this is going to represent some type of horizontal translation as opposed to the last one, which is a vertical translation. So h of x, and in this case what this is telling to is wherever there's an x in my function, I'm going to fill in an x plus 3. So I have to put x plus 3 cubed, and then I have the minus 6. So again, my x was right here. I have to put the x plus 3 in its place because that's what the it's telling me to do. Okay. Now, as far as this is concerned, we want to leave everything in like vertex form, kind of like we did with quadratics, where it was x minus h squared, and then we could have a k or something that shifts vertically afterwards. Okay. So right here, it's the same thing. We don't want to go ahead and multiply all this out. We don't need to. Okay, so what we're looking at right here is I can't combine anything on the inside. I'm not going to go ahead and raise it to a power and expand it because that would just make things more complicated. Alright, and there's nothing I can combine with this out here because I can't combine a number back here with something that's inside of a quantity that's raised to a power. So essentially my new rule for my function is exactly what's written right here. Okay, now as far as graphing it, again, it's just one of those things where with these, to graph them, you kind of just have to start picking x values and start filling them in a little bit. And as far as sketching the graph is concerned, graphing calculators, in all honesty, probably become a little bit more important when you're dealing with this. Okay, now again, just a kind of a quick reminder. Remember when we were working with quadratics, the base or the parent function was always x squared, which was centered right over the origin and stuff like that. When we're talking about x to the thirds and x to the fourths, okay, it's the same idea. An x to the third graph is kind of centered right around the origin right there. So what we're doing is, both this number here and this number here, we're applying translations to that parent function. So essentially what we're doing is we're taking this original x to the third graph and we're just shifting it around a little bit. Okay, now I probably put that in a bad spot. Alright, but what you can see there is the graphs of the two functions that we would happen to have right there. So I'm just going to go ahead and erase everything that's on there. Okay, but you can see looking at the graphs over here, this would be my original function in blue. Alright, and the new function that I came up right here would be in red. Okay, and you can see how my first function, x to the third minus 6, we more or less took that parent function and we just shifted it down 6 units. Okay, well, now with what we did to the last one, essentially we ended up, I believe it was x plus 3 to the third minus 6 was my h of x. Okay, now you can see that the minus 6 hasn't changed. That's why we're 6 units down from the x-axis, but we've also applied a transformation or a translation 3 units to the left. So from here we shifted everything over 3 units. Okay, so if you understand where the parent functions are supposed to be as far as centered around the origin and stuff like that, it makes this stuff a lot easier as we go through this. Okay, next we're going to take a look at what happens when we start reflecting things. Okay, now reflecting across the x-axis, reflecting across the y-axis. Now when you reflect across the y-axis, things become a little bit more confusing. X-axis is probably the easiest. Now remember, in your book, or I shouldn't say in your book, in your notes, if we want to reflect something across the x-axis, or in other words, when we had quadratics, if we took this and we reflected across the x-axis, it came down. So essentially what you were doing is you were just changing all the y values and making them negative. So really, when you're reflecting something across the x-axis, you take the entire function and you make it negative. So in this case, I want to take the function and make it negative, that means I'm going to take a negative and I'm essentially going to multiply it through to the entire function that I'm given. Okay, and we're going to call our new function g of x. Okay, so essentially what I do is I just distribute this negative all the way through to everything that's here, and the result that I get would be my new function. So negative x to the third minus 5x squared plus 8x minus 1. Okay, so this new function would represent a reflection across the x-axis, or essentially we took something that was to the third. Okay, so third would be something that probably looks like this, and we reflected it so now it would come down like this instead. Okay, now as far as where it's actually centered in this area, I'm not 100% sure without a graphing calculator, and in this case it doesn't necessarily say graph, so we're just looking at, hypothetically what we're doing is taking a function again that originally looks like this, and by reflecting it over the x-axis, now it becomes something that looks a little bit more like that. Okay, but in this case all you were looking for is to write a rule for g of x. Okay, now as far as the y-axis goes, this really isn't a whole lot more difficult, but if you're going to take something and you want to reflect it across the y-axis, essentially what we're doing is we're changing the x values. So what you do is you're going to fill in a negative x wherever there happens to be an x. Okay, now with parabolas, this was really easy because if we were trying to flip-flop things across the y-axis, those were already symmetrical, so it wasn't really going to matter. Okay, if we're taking something that looks like this and we would be reflecting it across, a y-axis or something like that, essentially you're going to end up with the same thing we did on the previous slide where we were reflecting across the x-axis. Is just going to be a little bit different format to get there. Okay, so again, what this is saying right here is my new function g of x is going to come from or result from filling in a negative wherever there happens to be an x in the original equation. Okay, now this one isn't just as simple as changing the signs and everything. You have to think a little bit. So like in here, if you take a negative and you raise it to the third power, it's going to remain a negative. Okay, so this is going to be negative x to the third. In here, if I square a negative, it's going to stay positive, so this just stays 5x squared. Again, if you square a negative, doesn't matter what it's going to be, it's going to stay positive or be a positive, so that's why we don't have to reflect that down here. We can just leave it as a positive. Here, negative times a negative is going to give me a positive, and then I still have a plus 1 at the end. Okay, so you can see how filling the negative in with the x has a little bit different impact than going ahead and taking the entire function times a negative and switching all the signs. In this case here, when I arrive at my result, okay, like in this case here, the negative didn't really change anything about what we originally have. We still have a plus 5x squared when we're done. Okay, but you can see how this factor, or this number, and this number right here, this term right there, those both change signs when you look at our final product. So you can see how that has manipulated our graph a little bit. Okay, now we're going to move down here a little bit. Okay, and now that we're done with the whole reflecting thing, the translating thing, now we're going to go ahead and take a look at what happens when we start stretching and compressing things. Okay, this one also says graph them on the same coordinate plane. I'm going to kind of do that after the fact here again, and we're going to describe g as a transformation of f. Well, the first thing we're going to do is we're going to apply the transformation that's given to us right here. So if we take 1/2 times the entire function, essentially what that's doing for us is we're changing all the y values or all the outputs by 1/2, okay, or by a factor of 1/2. So really what this is telling me to do is, it's pretty straightforward in here. I'm going to take the entire function, okay, to find g of x. I'm going to take the entire function times 1/2. Now this is very similar to when we reflected across the x-axis, where you're just taking an entire function times a specific factor. So when I do that, g of x is going to end up being x to the fourth minus 3x squared plus 1/2. Okay, so this is the new rule for my function if we are vertically compressing something by a factor of 1/2. Okay, so what that would look like in terms of a graph here. Okay, again, we are vertically compressing something. So our original function is actually in blue this time. Okay, and you can see again what we're dealing with is if you have an x to the fourth function. Again, it's very similar to a quadratic in that the parent function itself would just be sitting, centered right on the. They kind of look like a W or maybe even a flattened out parabola that would be centered around the origin. Here, both of these particular functions, the original and the one that we come up with as a final, are altered from the parent function. So that's why they're not centered right there. But what we're looking at here is you can see how the blue one, the original one, how every value in there has more or less, every y value, has been shrunk by a factor of 1/2. That's why the red function is not quite as spread out as the blue one is in a vertical sense. Okay, so again, if you're supposed to graph these on the same coordinate plane, it'd be one of the things where a graphing calculator would really help you out. Otherwise, what you're looking at again as far as graphing something like this, or even graphing our g of x function down here, is you're going to have to just start picking random x values to fill in to get points. And when you do that, it becomes a little bit difficult because you're not 100% sure, where your graph is centered and what exactly it looks like. So I would suggest using a graphing calculator, whether it's one of the ones that you borrow from me or that link that I provide you with on my website, to go ahead and get to something like that. All right. Now, if we look at something like this, and again, my original graphs keep popping up there as we go. Okay, what this one says is, graph them again and then describe g as a transformation of f. So in the last case, we took a factor of 1/2 times the entire thing, and what we ended up with was a vertical compression by a factor of 1/2. Now in here, you can see that we're taking a factor and we're putting it in with the x, which means it has something to do horizontally. Okay, and in this case, remember, horizontally is backwards, so what we're looking at here is probably a horizontal stretch by a factor of 3. Okay, and the reason it's, we can tell it's a factor of 3 is, remember, it's backwards. The factor that you are either stretching or compressing by goes on the bottom. So if you end up with a fraction, that means you're probably stretching by a whole number. If it's horizontal and the number that you get in here is a whole number, or the total thing is a whole number, that means that there was probably a fraction involved in there somewhere. So again, going back to those original notes, you need to figure out what your factor is or what your b is. Okay, now as far as working this one out to figure out what's going on, this one becomes, like I said, a little bit more complicated, because what you're doing is you're putting 1/3 x in wherever there happens to be an x in your original function, 1/3 x, and then we square it, okay, plus 1. Now if you want to actually simplify this, you can, and basically what it comes down to is, you can take the factor inside and the variable inside, so to speak, and raise it to whatever power it tells you to raise it to. And you can simplify or work towards something that is a little bit more simplified. So here we'd be looking at, obviously if you take x to the fourth, you get x to the fourth, but 1/3 to the fourth, if you take 3 and raise it to the fourth, I believe you get 81. Okay, so what you're looking at here is 2 times 1/81. All right, x to the fourth minus, here we'd have that 6, and then when you take 1/3 and square it, you get 1/9, and then you'd have x squared when you square it plus 1. All right, so you can see how this becomes a little bit more complicated if you want to arrive at an actual simplified result here. If I go ahead and I start combining stuff a little bit more here, -6/9 is going to be -2/3. x squared plus 1. So if you wanted to go all the way through and actually apply this transformation to go ahead and get a simplified result, this would be what your function looks like. The only thing is you can see in between here, when you start taking everything in here and actually raising it to the power that you're given, you can end up getting some weird numbers, and then you have to remember that you have to do that first before you start multiplying by the numbers that are out in front. Okay, so you're going to want to pay special close attention to that. But the main thing that we're looking at here is, because we have a fraction inside of here in our original instructions, we understand that this is basically stretching something horizontally by a factor of 3. Okay, so when we look at the actual graph that we get, we can see how the blue one is our original, okay, which we would have had up here. And after you apply the transformation, which would be represented by this one down at the bottom, you can see how the red graph has really stretched out horizontally. Okay, so again, in this particular case, if you can come up with the rule, that's fantastic. But it's one of those things where, and you probably would have to come up with a rule if you're going to try to be able to go ahead and graph both of these. Okay, but the big thing is, once you get the graph, can you tell, comparing the blue graph to the red graph, what's actually happened to everything that's going on here? Okay, and again, like I said, when we start talking about things horizontally, that becomes the part that's a little bit more difficult. Okay, because it involves input values as opposed to just taking the entire function times something. All right, now the last thing here is we're just going to go ahead and we're going to combine. Okay, we're going to go ahead and we're going to combine some different transformations together, and we're going to write rules for how this is supposed to work. Now, this again should be similar to what we did before, and most of us tended to have a lot of success when we go ahead and doing this. Okay, so our original function, I'll write it down here a little bit, f of x equals 6x to the third minus 3. Okay, so what we're going to do is we're going to compress it vertically by a factor of 1/3, and then we're going to shift it 2 units to the right. Okay, so essentially what we want to do is we want to take the whole thing, the whole function, times 1/3, and then we're going to 2 units to the right, so it's backwards or kind of opposite. Alright, so actually I would have to put the minus 2 inside with the x. So if you give me a second here, I'll try to erase this a little bit. Start over. Okay, so because we're going 2 units to the right, it would be something that looks like this. Okay, so we'd have to do a little bit of shifting there. Now the nice thing about all this stuff is when you actually apply those transformations, again, we're compressing vertically by 1/3, meaning we take the whole function times 1/3, and then 2 units to the right is a minus 2 in terms of the x value, so that's why we fill it in with the x. So if we're actually going to make this happen, okay, we're going to take, and I'll write my new function as g of x, 1/3, okay, essentially times the whole thing. So we're going to go 6, then in with the x, I'd have to put minus 2 to the third, okay, and then I have minus 3 behind it. Okay, so from here, again, you're not going to be able to do anything inside of here, but we can take the 1/3 through to everything else. So my final kind of simplified rule is going to be, if I take 1/3 times 6, I'm going to get 2. So 2 times x minus 2 to the third minus 1 when I go ahead and take that 1/3 times the 1. So my new rule, or my new function, is going to look something like that. Okay, and that's just an example of applying multiple factors to a particular problem. Okay, here's another one. Okay, we start with our original function, f of x, and it's the same thing that we had before. Okay, now in this case we want to reflect across the y-axis, which means against the y-axis we actually change all the x values and make them negative, and then we want to go 2 units down. Alright, so it's going to look something like that. So if I actually input that stuff, or apply those transformations, alright, I have 6, I have to put a negative in there. The third, I still have my minus 3, okay, and then behind it, I take the entire function minus 2, which is going to shift everything down. Okay, now again, because we're starting to deal with stuff that's cubed, we just have to think inside of here. If I take a negative and raise it to the third, my result will still be negative. And what I mean by that is think about negative 3 to the third. Okay, 3 to the third is 27, but if you're going negative 3 times negative 3 times negative 3, you can see how your end result is going to be negative. Alright, so what I do with that is I actually take that negative I know I'm going to get, and I'll write it like this. Okay, and then I can go ahead and combine these two, get minus 5. So this would be the transformation that reflects what's going on there. Okay, now again, remember, when we started filling negative values in, when we had quadratics, it never mattered, because anytime you square something that's negative, you always get a positive. Alright, so that's one of the things with this entire lesson that you have to make sure you pay attention to and are aware of, is that if you have something raised to an odd power, like a third, and it's negative, that negative is actually going to, turn into making the entire thing negative after we're all done. Okay, now again, this was one of those where the lesson itself was kind of a lot of review stuff. There are a few new aspects to it, and you're using functions that have exponents that are higher than just something squared like we'd used before. But if you take notes on that, I think it was on the third slide, that chart that talks about how you transform everything, you should have a lot of success with this particular lesson.